Up till now, we've covered several different techniques which are involved in the differentiation of functions and trig functions. They're all important techniques, but what we need to be able to do is differentiate slightly more complex functions that may come up. And that's where today's video is going to come in handy, because what we're going to look at is a technique called the chain rule. Now, the chain rule is something that allows us to look at differentiating what is essentially a composite function, i.e. a function within a function. So something that's not quite as simple or straightforward as we would cover up to this point. Now, when we are differentiating it, composite functions have this format here, so f of g of x. And when we're differentiating using the chain rule, this is the format it takes. So d by dx of f of g of x, so the derivative of our function, which again is a composite function, equals f dashed of g of x times g dashed of x. Now that looks like a slightly more complex formula than you want it to, but actually it's fairly straightforward if you break it down into two simple steps. The first step being differentiate the outer function, so whatever the f is, and keep the bracket within it the same, so keep your g of x the same. What you then do is differentiate this bracket, so differentiate the g of x, and multiply everything by it, so multiply the entire thing by the overall derivative for what's in here. It is actually quite straightforward when you break it down, and the best way to illustrate exactly what I mean to you and exactly what I'm describing is by looking at an example. So let's imagine the question said to me to differentiate the function y equals cos of 5x plus pi over 6. Now this takes the format. This takes our format of f of g of x, because what we're able to say is that my f, so the outer function, is equal to cos of x, so the cosine function, but my g of x is equal to 5x plus pi by 6. It's equal to this part here within the bracket. So now that I know what the f and what the g parts are, I'm able to use the chain rule to actually differentiate this. So I'm able to use the fact that d by dx of f of g of x equals the f dashed of g of x, so the derivative of the outer part first, times the derivative of the inner part. So what I can start by doing is looking and differentiating the outside thing completely, then differentiating what's in here. So what I can then say is fine, so my dy by dx equals, well, the derivative of the outside part, which is the cosine, so derivative of cosine is minus sine. So the derivative of that minus sine, and you keep the bracket the same, just as we said within our two steps at the start. So it's minus sine of 5x over pi by 6. I then multiply by the derivative of my g of x, or the derivative of whatever's in this bracket here. Now it's 5x plus pi by 6, so the derivative of that is just quite simply 5. What I can then do is simplify my answer and get negative 5 sine of 5x plus pi over 6. So I've taken the derivative and you've done your chain rule to get it. And it's actually quite a straightforward set of steps. So just remember, outer function first, keep the bracket the same, multiply by the derivative of whatever's in here. Another example for you, imagine I've got the function y equals sine of x squared plus 1. So the g of x part within it, so the part within the bracket, is now no longer just a simple ax plus b. It is no longer just a simple function like that. But that doesn't mean the chain rule changes. That still means that my d by dx of f of g of x still takes the exact same format as it did before. It still takes derivative of the outer, with the inner part there, times the derivative of the inner part. It still takes that. The only difference is my inner part is a slightly more complex function. So we start the same. We say fine, so dy by dx. Derivative of the outer part, so derivative of sine. Derivative of sine is just simply cos. So it's the dy by dx equals cos of x squared plus 1. Great. We then multiply it by the derivative of what's in here. So the derivative of this part here. Derivative of x squared plus 1 is 2x. So then I can say fine, so my derivative is equal to 2x cos of x squared plus 1. And that's me done. At that point I can safely say, right, I've got my derivative. Yes, it's a slightly more complex one. Big deal. We're going to get that in maths. The only difference is I'm going to end up with more x's. Now, this is when we have functions that look like this. However, we can up the ante and look at certain special cases that take similar formats to powers of linear functions, things we've covered before. And we can have a special case where it's a function to a power. So the linear case that we had before was when we had something that was of the form ax plus b to the power of n. This is when the ax plus b is no longer just a simple linear function like that. It can take another format. And to do that, we times the whole thing by the n, so whatever the power was, reduce the power by 1, keep the function the same, then multiply by the derivative. That seems like a lot to throw at you, but again, it's actually quite straightforward once you demonstrate it with an example. And that's what I'm going to look at here. So what I'm going to look at is finding the derivative of y equals the square root of 2x squared plus 3x. Now when we covered this kind of thing before, our first step was always to put it into a differentiable form. Square root, we have to write it as a power, remember. And writing the square root as a power is to put it to the power of a half. So we get 2x squared plus 3x to the power of a half. Now this takes this format here. It's some function that's no longer just ax plus b, so it's 2x squared plus 3x, to a power, which is a half. That means we have to follow this format here. So to get dy by dx for this sort of one, we quite simply follow the same sort of deal we did there. So we bring the power down, we make it a half, keep the bracket the same, 2x squared plus 3x, reduce the power by 1, so a half goes to negative a half, and then we multiply the whole thing by the derivative of the bracket. Now before with the linears, the derivative was just simply the coefficient here, the a. This one isn't. This one has an actual function dependence on x, so we differentiate it like normal. So derivative of 2x squared, bring the power down, reduce it by 1, we get 4x, and then plus the x just simply becomes a plus 3. Now we're at this point, we have to simplify the whole thing. Negative power, it goes down to the bottom. Now a key thing to watch here, and it's a mistake that's quite frequently made, the power is with this first bracket, not the second one. So the negative a half, putting this one on the bottom, has no effect on this bracket here. So what we'd end up getting on the bottom is the 2 times the 2x squared plus the x to the half. But this bracket here is multiplying the whole thing, so that stays on top. So that stays as 4x plus 3. So we can then change our power of a half to a square root again, and have 4x plus 3 over 2 times the square root of 2x squared plus 3x. Yes, it looks like a slightly more complex function, but actually it's the same general steps as this in using the chain rule. The only difference being, again, we've upped the ante a little bit by putting a slightly more complicated function. But by this point, we should be able to differentiate those. Those should not be an issue for us to take from 2x squared plus 3x, find the derivative and get 4x plus 3. This is the level we need to get to for now. So these are the basics of differentiation we've looked at in this unit. When we look at the next unit, what we're going to look at is how we apply these. So what's the point of us doing these if I don't tell you what we use them for? And that's what's going to get covered in Unit 3.